This PowerPoint is over vibration and waves for simple harmonic motion. All right, so the topics we're going to be discussing is Hooke's law. Then we'll talk about elastic potential energy, comparing simple harmonic motion, which is SHM, with uniform circular motion. Position, velocity, acceleration is a function of time, the motion of a pendulum. These are going to be all the things we discussed. So the first thing, if an object vibrates or oscillates back and forth over the same path, each cycle will take about the same amount of time, which we call period. That's where we get that term periodic motion, is because the amount of time it takes to complete one cycle is going to be a period. So that periodic motion is going to be simple periodic motion, just simply because there's only one dimensional of as it vibrates back and forth, and we get a restoring force that's going to be linear, and we'll talk about that in a little bit. All right, so we assume that the surface is frictionless, okay? So that if it's frictionless, then that means it'll oscillate back and forth and continue with the same amount of distance on either side. If there is friction, it'll actually get less and less distance that it travels on each side, which we call dampening. But if it doesn't dampen, then that means it keeps the same range, what we call amplitude. The maximum displacement is going to be the amount of amplitude. All right, so as the spring stretches or compresses, there is a restoring force that pushes it back to that equilibrium position. That equilibrium position is the point where it's neither stretched nor compressed. Now keep in mind, as it's oscillating back and forth, even though it gets to an equilibrium position where there's no force applying to it, it's still moving, which means it's still going to be moving forward. And as it moves forward, then the spring starts pulling back. And then when the spring stops it at this end and pulls it back, then that means it's not moving, but we have a force being applied to it. And then by the time it gets back to this equilibrium position, then it's moving again, but there's no force. And then as it goes past it, then we have a force with no motion. So we get this oscillation back and forth where we have motion stopping and then no motion, and so on and so on. All right, so Hooke's law says that the spring force that's being applied is going to be equal to negative kx. Now, negative k, the negative simply means a direction, which when we start talking about energy here in a second, the negative really doesn't matter. The k is just that's the spring constant of this spring. That's the constant that allows us to describe how the force is going to be administered over a distance. And then we got a distance of x. Now, if you notice, this is a linear equation. This is a linear function. So the more distance you pull it, the more force you get. What would be not simple harmonic motion would be if you have, let's say for an example, an x squared or square root, something that you would have some sort of power on this x. That would not be simple harmonic motion. So the hallmark of a simple harmonic motion is that the force is linear according to the distance that it travels away. All right, so as it travels, you get more force being applied. That means more acceleration as it comes back. All right, so the minus sign indicates the direction, as we talked about. So as the position goes in the positive direction, the force is in the negative direction, and vice versa. As the position's in the negative direction, the force is going to be in the positive direction. And the main idea is you always try to get back to the equilibrium position. But the reason it doesn't stay at the equilibrium position is because it's moving when it gets to the equilibrium position, which is why it oscillates back and forth. All right, so this is what Hooke's law says. Now, to describe a couple of terms, a couple of variables that we're going to be using on a constant or regular basis, it's going to be the spring constant is going to be the K value, all right, and that's in terms of newtons per meter. The displacement is going to be x. I know usually we use a delta x, but just to kind of simplify the equation a little bit, we'll just say it's a position relative to the equilibrium. We'll make the equilibrium position 0. So that means x is going to be the distance from the equilibrium. And then the amplitude, that's the maximum displacement. The furthest it gets from the equilibrium position, we call that amplitude A. Then we have the cycle is a full to and fro. So let's say we start here. As it goes this way and back this way, that is one full cycle. Now that makes sense when you're starting from one extreme and then you go all the way to the other extreme and back. What doesn't make sense, what people kind of get confused on, is if we start our cycle in the center. So let's say it's already moving and it's at the equilibrium position. That if it goes to the left and then back to the right, that is not a full cycle. It has to go all the way to the right and then back to its equilibrium position in order to make one full cycle. All right, so keep in mind, a full cycle is all the way to the extreme and back to the other to get to your initial starting position. All right, the next one is going to be period. It's a capital T. That's the amount of time per cycle, the amount of time per cycle. And then the last one is going to be frequency. The frequency is the number of cycles per second. Now, what you'll notice between period and frequency is they're very much related. Period describes the number of seconds every cycle. The frequency describes the number of cycles every second. Now, why do we have two different terms? Because those are effectively, they're reciprocals of each other. So if you take the period, take 1 divided by that, that gives you the frequency. So why do we even have two terms when you could just take 1 divided by period and get frequency, 1 divided by frequency and get period? Well, generally what has happened over the years is scientists start describing different things and they describe it in different terms. So we got both of these terms. Now, why period versus frequency? Well, period kind of describes something that takes a really long time to make one full cycle. We'll say, for example, the Earth as it rotates on its axis. When the Earth rotates on its axis, it makes a little bit more sense to say, well, how many seconds does it take to complete one cycle? But when we talk about frequency, we're talking about something that oscillates very fast. So let's say an atom that vibrates back and forth as it oscillates. It oscillates millions and millions of times every second. So to say, well, it takes this many seconds to complete one cycle, that doesn't really make much sense. It makes more sense to say, well, it completes 30 million cycles every second. So the period is measured in seconds, but 1 over seconds for frequency is actually what we refer to as hertz. A capital H, lowercase z is going to be the units that we use for, but it's called hertz. All right, so if a spring is hung vertically and only changes it'll change its equilibrium position, which is the point at which the spring is where the net force is 0. All right, so the equilibrium position for the spring originally is right here. So if we start oscillating an object that is not there, pretty much, then that basically is pointless. But if we attach a mass to it and we let it down to where it's not oscillating, it's just stationary, then that now becomes its new equilibrium position, because now we have a force of gravity pulling down and the spring force pulling up, and those two forces are now balancing each other. All right, and that's what we call our equilibrium position. Now, with that being said, when we start talking about energy, all right, we start talking about gravitational potential energy, spring potential energy, kinetic energy, and all those things. When you have a mass that's on a spring like this and it oscillates up and down, effectively the spring is going to take into account the equilibrium, or the force of gravity at its new equilibrium position. So when we do conservation of energy of this object right here, we do not have to take into account gravity because the spring force is already accounting for that. All right, kind of weird to think about, but effectively, just to kind of simplify some scenarios later, when we have a spring oscillating up and down, that we really only have to take into account the spring potential energy and the kinetic energy as it's oscillating. We don't have to, even though it's changing height, we don't have to take into account the gravitational potential energy because the spring already accounts for it. All right, so any vibrating system that can fit this model, meaning the force, the restoring force that's being applied, is going to be equal to negative kx, meaning the negative, the force is bringing it back to the equilibrium position, and the force is linear with respect to the position, then that will give us a simple harmonic motion. So this equation right here is what a restoring force has to fit this equation in order for us to call that a simple harmonic motion. It has to be a linear function between position and force. All right, so moving a simple harmonic motion, we call it a simple harmonic oscillator. So the potential energy of a spring is given right here. All right, if you remember talking about the potential energy of a spring, it's kx squared over 2, and that's because the force is a linear function, so it's a straight line that goes up. So in order to find the area, which gives us the work of a force versus position graph, then it gives us a triangle, and that's why we get that 1/2 right there. For the total mechanical energy, if we're dealing with an object that is completely horizontal, so we're not taking into account gravity as it oscillates horizontally, and really even if it oscillates vertically, because that spring potential energy takes into account the gravitational potential energy. We don't have to have a separate term for that. But we basically transfer from from spring potential energy over to kinetic energy and back and forth. It'll oscillate back and forth between the two, and the total amount of energy will be encompassed in this. Now, in order to figure out how much energy a system actually has, then we're going to take one extreme or the other. One extreme would be where the position is all the way stretched and we have zero velocity. Or the other extreme would be where we have the maximum amount of velocity, but we have no stretch or compress of the spring. That way it kind of simplifies our equation to figure out how much energy there is by only taking into account kinetic or spring potential. Now, if we get somewhere in between there, then we have a little bit of kinetic and a little spring potential, and we got to take both of them into account. All right. So total mechanical energy will be conserved as long as we have no outside dissipated energy like friction, and that's something we stated already, that we have no frictional forces being applied. But as long as there's no friction being applied, then that amount of energy will stay constant, just slosh back and forth between the two types of energies. All right, so if a mass is at its limits, then we call it the amplitude, right? So that the amount of potential energy, spring potential energy, is going to be K. Remember, this is Kx squared over 2, but since we're at its maximum, that's what we call the amplitude. And that's going to be the total amount of energy in a system as it oscillates back and forth. Now, that's our total because the amplitude is a constant. All right, the amplitude is a constant because that's the maximum it's going to get to. Now the position will change, and you'll have some gravitational, or I'm sorry, some spring potential and some kinetic energy, but the total amount of energy will be equal to that maximum amount of spring potential energy. Okay, so in order to figure out how much speed it's going to have at this point right here, then what we could do is we could take that spring potential energy and then set it equal to the amount of kinetic energy, because we're going to lose spring potential energy and then we're going to add kinetic energy, and then we could set those two equal to each other in order to figure out what the maximum speed is going to be. All right, so the total energy, Ka squared over 2, we set those equal to each other, so we can actually figure out at the maximum speed is where we have no spring energy anymore, and then we could solve for that v. All right, so solving for the velocity. All right, so this equation right here, this is basically the velocity at any given point. And you can kind of see where we get this from. All right, so the 2 is going to cancel out of here completely. We divide both sides by k. And then we bring this x squared to the other side. So dividing, I'm sorry, we don't divide by k. We bring this over here, we get ka squared and minus x, or kx squared, and then we bring that k to the outside, and that gives us a squared minus x squared. And then to solve for our v would divide by mass. Remember, all the 2's are going to cancel. Divide by mass, and then to solve for the velocity, we square root both sides. And because we square root, we always get a positive and negative. And the reason we get a positive and a negative is because if we're on one side of the equilibrium position, then it's moving in the positive direction. If it's on the other side of the equilibrium position, it's moving in the negative direction. So we get two possibilities. All right, so to find our maximum, we set basically where x is 0. All right, so where x is 0, that's going to be our maximum displacement. Our maximum velocity, where we're 0 displacement, and then we have this a squared, we square root that to bring it out, and we get a square root of k over m. So that's going to be for any system that we have. For any system that we have, our maximum speed is going to be equal to the amplitude, square root of k over m. All right, so the acceleration, what is the acceleration as a function of displacement? Well, we got our force equation. Force is going to be equal to negative kx. But if that's the only force being applied, then that means it's our net force. If that's the only force being applied, then that's going to be our net force, which is equal to mass times acceleration. So then to figure out the acceleration with respect to position, then we take this mass to the other side. We get negative k divided by m times x, and that gives us our acceleration. The maximum acceleration is where we're going to be at our maximum displacement. Now remember, our maximum displacement is actually where we have 0 velocity. So if you think about this, our position and our acceleration are at their maximum at the same spot, but our velocity is at a minimum at that spot. Our velocity is actually going to be at a maximum when x is 0, and as you can see from this equation, where acceleration is going to be 0 also. Now what you may notice is that acceleration and position are in opposite directions. So if you were to look at these two if you were to graph these with respect to time, then if x is at a positive position, then acceleration is going to be a negative acceleration, which hopefully kind of makes sense because the acceleration and the acceleration and the force are in the same direction. So if the force and position are in opposite directions, that means the acceleration and position are also going to be in opposite directions. Okay, so now that we've talked about simple harmonic motion, let's kind of look at this scenario right here, because what I want to show you is we look at this Vmax equals a square root of k over m. So that is modeled by simple harmonic motion. Now I want to look at the motion of a circle, of an object that's moving in a circle. So if we look at the projection onto the x-axis of an object moving in a circle of radius a at a constant speed of Vmax, find the x component of its velocity as it varies. Okay, so we've identified a couple of things. You got Vmax, which we already think we know what that is. Why are we calling the speed as it goes around Vmax? We'll talk about that in a second. And radius a. Why don't we use a for amplitude? Well, let's look at this. So we're effectively going to be looking at the x direction, right, as it goes around. So if we're just looking in the x direction of this, the x motion of this object as it moves around in a circle, then that means everything that we have that moves in 2 dimensions, like the radius is going to be in 2 dimensions. All right, so as it comes around, it's going to be up and to the left or up and to the right, but we just want the right part of it and look at just the rightward part of it. Another way you can think about this is taking the circle and turning it horizontally and just looking at it from 1 dimension, where we just look at the x motion of it. All right, so if we're just looking at the x motion of the velocity, then that means the x component is really all we're looking at. The x component is going to be 0 over here, but up here it's going to be at its maximum amount, where it's going to be completely in the x direction. And that's why we call the actual velocity x max. All right, now again, over here the velocity is upward, and if we're just looking in the horizontal direction, then that means something going in is not, there's no horizontal component to that, there's no x component, so it's going to be 0 in the x direction. But up here at this point, it's going to be all in the x direction, so that's where we get our maximum velocity. All right, so let's look at the velocity right here. All right, so the velocity is going to be the maximum velocity, that's the hypotenuse, sine of the angle, right? So that's going to be the component of the velocity we're going to be looking at. All right, so what about the radius? All right, the radius. Now we call it amplitude. Now you think about this. The amplitude, the maximum we're going to get away in the x position. All right, if we're looking in the x direction, the maximum we're going to get away is the full radius of it. Now, so that means over here, if we're looking at it, then that means that that object is as far away from the center as it can possibly be. So that's its amplitude. Now, when we get up to the top here, you'll notice that if we were looking at it straight on, that the center and the object is in line with each other. So as far as the x direction is concerned, there's no difference between the center and where it is there. So it's basically at its equilibrium position at that point when we're looking at the x direction. All right, so the x component here, all right, the x component is going to be, we have the amplitude here, and to find that x component, let's figure out what this other side is, so we can kind of use a little bit of trig on this. All right, so that other side is going to be a squared plus b squared equals c squared, right? All right, so we have this side is x, this side is a, so this side right here is going to be a squared minus x squared, and then the square root of that gives us this. Okay, so sine of the angle, keep in mind sine of the angle is going to be equal to opposite over the hypotenuse. So that's square root of a squared minus x squared over a. And what we're going to do is we're going to take that, we're going to plug that into our velocity equation. So we're using the position and the velocity, and we're relating those. All right. So then we take the Vmax equals a square root of k over m. So that's our model for simple harmonic motion. Let's plug that in. And what you're going to notice is you're going to notice something very similar to what we've seen before. All right, so you'll notice here that the a will actually cancel from both of these. The a will actually cancel from both of these. And what you're left with is you're left with this equation. Now, hopefully this equation looks very, very similar to what we've seen before. And that means that because that looks like simple harmonic motion, then that means an object that's moving in a circle is modeled by simple harmonic motion. The same simple harmonic motion of a restoring force as it's oscillating back and forth matches the x component of an object moving in a circle. So we can actually use some of the mathematics we have for this circle in order to apply to simple harmonic motion. All right, so identical to simple harmonic motion, where if you remember, v equals v max square root of 1 minus x squared over a squared. All right.